I've put together a few things. These are borrowed slides from other things I've done in the past. We've mentioned worked on the National Children's Study, their data linkages component. They never really did any data linkage for that. Of course, the National Children's Study is not around anymore, but that's not the reason why. For it, they really wanted people to explain what the concepts of data linkage, the different ways it could take place. So I've kind of put together some slides of things where myself and Mike Sinclair had tried to explain some of these concepts to people who knew they wanted to combine data sets but really had no concept of the difficulties. But I think I'd just start with, and Jerry covered some of these things, just what's the purpose of combining data? And just in a very simplistic sense, if we just think of the data frame that we usually have, the rows are our cases, the columns are our variables. Sometimes you're combining information to increase the number of rows, increase the sample size, get better coverage, more power for your analyses, or you're increasing the number of variables. And record linkage, statistical matching sort of deal primarily with that, although as Jerry was talking about, you could try to attempt to do both of these things. So there's the length of the file, the width of the file. What are you trying to accomplish? And there's different reasons for doing these different types of approaches. I think early on, Joe had mentioned basic ideas on just generally combining information. If you have dual frames, sort of like a landline and a cell phone frames, you get better coverage, at least of people with phones. For increasing the sample size, I wouldn't think of it as combining data as much, but meta-analysis has been around for a while, and that's what people are trying to do, is effectively increase sample size. A current hot topic is combining probability sample with a non-probability sample. This can be done for coverage as well, but at NORC we have an online panel, Amerispeak. It's designed to produce national estimates, and sometimes people want subdomain estimates, young black males who live in urban areas. Well, we have some of those people represented in the panel, but there might only be 500 or so that we get responses from, and that's not enough. So sometimes we will supplement that sample with a targeted list of people that we are fairly certain fit the criteria. This is a relatively inexpensive way to collect data, but it also creates other problems. How do you combine these things in a way that represents the data? But those types of combining are a lot more about, usually people look at it as, how do I reweight the file so that it's representative? But other times, apologize, I have an incomplete thought on my bottom bullet there. I started thinking of an example where epidemiologists wanted to match in air quality measurements. They had roughly gotten them at a zip code level, and they wanted, say, to match in some ACS variables with those air quality measurements. That brings about another problem, which is probably a topic for another day. But let me move on to just talk about, in general, as we're trying to explain combining data, in particular the data linkage problem, which, as I say, and I'm thinking of as more increasing the width of my file. You could think about it in a number of ways, and mostly today we've been talking about, entity level linkages. You could do area level, just, group statistics, or some people might even just match, say, census tract estimates with a person's information in a survey, so it could be an individual to an area type of match. All of these things come with various problems. I don't want to make them seem all that simple. And I've also seen in a lot of applied papers where a lot of the difficult issues are ignored. As I think Bill was saying, people do the record linkage and they want to believe that that's all they need to do. There's very little thought about incorporating the errors that might be into the analysis. So mostly we're talking about this, down on the left side, the record linkage and statistical matching, and that's what Jerry talked about. I just kind of wanted to try to bring up in a complete picture of all the issues that might be out there. And this is, my next slide is more just a, trying to give a visual diagram of the types of things Jerry was talking about. So the typical setup for statistical matching, although it doesn't have to be this way, you've got records or measurements are at the same level, so we can think of these as individuals. You've got two data sets. I've labeled them here, two samples, but it could be a sample with administrative data. But you believe there's little to no overlap between the two files. There could be overlap, which is going to complicate the issue some more. But as Jerry was mentioning, the typical statistical matching would try to take a record from sample 1 and match it to a record in sample 2 using some type of say, distance or similarity measure. And that's very much, as Jerry described, a hot deck type of macro. You just have two different using the same ideas there. As I said, I created this slide a while ago, and when I was putting this together and I was looking at it, I knew it reminded me of something else. And one thing was, if it was legitimate to just stack these files together, and Jerry talked about this a little bit, you could essentially just treat this as maybe a missing data problem, where now I just need to have a model where I can fill in the upper right and the lower left corners, and then I not only have increased the width of my data, I've gotten better length. But there's a lot of issues in that. Should you even just throw two samples together, especially if they come from complex samples? As Don was talking about earlier, are these X values, are they harmonized? Are they, if they're from two different samples, are they measuring, making measurements in the same way? But one of the reasons it reminded me something, it went back to a JPSM distinguished lecture. I think it was back in 2011. In that time frame, it was really Ray Chambers was the main speaker, but Mike Elliott was one of the discussants, and he threw down a concept that I have not followed a lot to see if much has come of it, and it sounds like Jerry hasn't heard of it, so maybe a lot hasn't come of it. But I thought it was an interesting concept, and I've overly simplified it in the following display. So he talks about combining multiple complex surveys. So in the display, you can think about it as three files, and in survey 1, you've got X and Y variables. Survey 2, you have the X and the Z variables. Survey 3, you've got Y and Z variables. And these were all done probably in different complex, the sample designs on these are different. So he talks about first taking each of those data sets and using the relationships in there to create synthetic data, and it would be a synthetic data set that would have the look and feel of a simple random sample. because if you had simple random samples, you could stack these things together. So he would say, create the synthetic data. Now I can put them together, and in my diagram, I just have to now fill in that off diagonal. And you could use, say, multiple imputation methods to do that. So it's a simple concept. On the other hand, implementing it creates a lot of problems, which I think Jerry also sort of started covering those things. If I'm creating the synthetic data sets, I need to do those. I should do those multiple times. And when I put everything together and then I start doing multiple imputation, well, I need to do that multiple times. So what started out as simply 3 files, you could have, 36, 64, whatever data sets that you would have to analyze. They'd all be fairly representative of what you want to do, but now you've got the 36, there's multiple analyses, and at the end, you have to figure out how to put them back together. And it's really the variance estimation, as Jerry has pointed out. But as I was saying, this was, I have, like Jerry, I don't have a lot of references. This was in 2011 when Mike gave this. I believe it was his student, last name Dong, who it was the PhD dissertation. I have not followed this to see if they've put this out in the literature or if they were just working out sort of the theoretical aspects. They sort of talked about it as a principled procedure for combining multiple complex surveys. Anyhow, I don't know, Jerry, if that gives you an inkling of where to look for doing something like this, but that's one thing I've heard about. And anyhow, that's all I have to share. It was a very good summary by Jerry. Especially liked the sensitivity analysis ideas, because the conditional independence assumption is something that you should be checking. I did want to note that the Italian statistical agency, they tend to do a lot of statistical matching, and a couple of the people from there have written a book on statistical matching. And they made the bad choice of making an acronym about the conditional independence assumption, calling it the CIA, and I just think it's a bad idea to mix the CIA with a problem on linking records together. Anyhow, that's all I have to say. Thank you.
Thank you, Ed. Right, I'd like to open it to the floor. Does anybody have any questions for either Jerry or Ed?
I'd like to ask both of them.
The mic on.
I'd like to ask both of them if they have any recommended references for a specific problem that I'm facing. We are trying to link individual establishments and a census of establishments to parent companies for only some of those establishments. And we have a list of parent companies we're interested in, and we've tried to find all their establishments in our census, but we know we're doing it with error, and we know something about the pattern of what kinds of errors we're making. But we're trying to give some resulting estimates of employment for these establishments once we flag the ones that we're interested in. And since this comes from a census, the census isn't used to making estimates that have any kind of variance or standard error estimations. And we know that we've got some non-sample errors, figuring out which ones we're interested in flagging. So it very much is a problem in this vein. And so I'd like to ask if there's any references you can think of that would give us the best practices of estimating this non-sampling error.
This is Jerry. Can I? Okay, that's good. Sorry.
Go ahead. We can hear you.
Okay, I was worried I was stepping on Ed.
No.
Okay.
Go ahead. It's all yours, Jerry.
Oh, okay. All right. So if I'm hearing you correctly, it almost sounds like you're in kind of almost like a record linkage situation, and with noisy variables, and it's kind of. And if I'm wrong about that, then I apologize. But it's sort of funny that I have a former student who finished last year, PhD last year, and her thesis was all about record linkage ideas. And one of her projects, we actually tried to link manufacturing establishments that had undergone energy audits to the census data, to the Census of Manufacturers data, because that allows us to get a sense of whether these energy audits actually, had any impact downstream in terms of their costs of energy usage and things like that. And you can't do the linking exactly because of privacy reasons, and so you have to do an inexact linkage. And the variables that you link on are things like employee size and sales and these sorts of and industry code and it turns out that a lot of those variables are quite different in the audit data and the Census of Manufacturers data. Even for companies that are unique in state and NAICS code. And so it kind of creates a conundrum about, how are you going to do this matching when you have these inexact matching variables that are clearly measured with error on the files. And anyway, so we have a paper that appeared in Energy Policy, which if you send me an email, I'm happy to point you to, but it might give some ideas.
Actually, as I listened to that, one thing came to mind, and we're probably talking about the same person. Bill, both of you were in the JSM session last summer. What's her name, Jerry? She gave a talk on her methods.
Nicole.
Yes.
Yeah, that's her. That's right.
Very good. Right, and I'm not sure if that's the actual application, but your description reminded me of what I heard her talk about at JSM. So, very good. And if Bill says it's good, it's good.
Super high praise.
Yeah.
Any other questions?
I could make a comment.
Yeah.
Can I grab a
You want, either way, you can come up.
I'm familiar with some of the work of D'Orazio and Scan, who wrote the book on statistical matching. And I've written software that I sent to them to do some of the things. And they brought up the issue with dealing with 3 or more files. And it's a relatively straightforward software problem if you go at it right. And so the solution that I had, I did give to them, and they were able to run it. And the other thing that they did in their KOS paper is they put other external restraints on. Some of them were based on the understanding of their data. So, like, if they had, like, a variable that took, like, 4 values, they're looking at margins, maybe they knew from past experience that one margin had to be larger than another. And they were able to put that in using an EMH algorithm that I had introduced. And what happens is that you have to use convex constraints, and that doesn't sound like a convex constraint, but they were able to formulate it as it was. Once you use the convex constraints, you can bring in a lot of external information that you wouldn't have been able to previously. So there's a way of dealing with 3 or more files. The only problem is you really want to think about is everything logically consistent? And if it is, then you start playing with the software and some empirical examples. But the software is quite straightforward to write as a generalization of what you do with two files. It's this type of log linear contingency table building things.
This is Jerry. I think first somebody on the phone doesn't have their mute button on, so it's I hear a lot of rustling. But anyway, thanks, Bill. I think actually taking some of your ideas and the Italians' ideas of putting constraints on parameters of these joint models and sort of combining that with some of these ideas potentially, if we can, we have data, microdata. That seems like a really really useful.
I have another question related to the example that you mentioned. Predicting the joint distribution through non-probability or other data sources. In the way you guys did it, or the way you doing it,
sorry, I don't mean to be rude, but unfortunately I can't hear anything. And also, again, there is somebody who's out there on the phone, does not have their mute button on, so we hear all sorts of movements. And if they can mute, that would help a lot.
It's coming up here.
Yes, go ahead, thanks.
Okay. So in the example that you mentioned with the civic science data, going out there and taking a non-probability sample with a lot of, I guess purposefully fielding the joint distribution that you want, in which situation would that not work? I mean, for the way you've been using it, and I will look up your paper, but I was wondering if you can share a little bit constraints to that idea, under which conditions that would or would not work.
Okay. It would. Well, we have to think carefully what we mean by work. So, what I think of work as, can I do better than if I did not have that information? If I just made a conditional independence assumption, for example, right, which is what most people would do by default. So that maybe I'll take that as work. So it can do worse if that conditional distribution in that civic science convenience sample data is just really a terrible representation of the conditional distribution for the survey you're trying to fuse into, or surveys you're trying to fuse, because it'll push you. It could push you towards imputed values that really shouldn't connect up with what the Z looks like at all, right? So that's the kind of thing you worry about. That's a kind of an unverifiable assumption as well, but maybe it's a little bit sort of weaker or less unpalatable to be really diplomatic about it. Less unpalatable than a pure conditional independence assumption across everything. So that's the issue. It's all about how well that conditional distribution represents. If you're talking about sort of, if I just stack all the data on the bottom and I don't worry at all about trying to make the margins of X and Z. So if you have file B, you're stacking data on the bottom of file B. You're trying to make the margin of X and Z look right, and because you have a model, you're going to build a model for Y, Z, and X from the civic science data, and you get this non-representative data on X and Z. You get a lot older people, and you stick all those people at the bottom of file B, and then you estimate some joint model, for example. It will throw things off. The fact that you've added some non-representative X distribution will muck up the marginal distribution of X that you fit in that joint model, which will then muck up the imputations that you wind up getting. It throws everything off. But if you kind of cheat, the way we do it is it's real simple. We just basically say, all right, well, we want to make sure our distribution of X and Z in this augmented data that we make matches the distribution that was in the file we want to match to. Well, we'll just bootstrap the X and Z's that we observed in the file, right? And so we create basically a copy, with the size determined by how much strength we want that extra information to bear. If we don't trust it that much, we might not make a lot of copies. If we trust it a lot, we might make a huge copy. But anyway, we copy this so that distribution of X and Z stays basically exactly the same. And then we create new Y's from whatever conditional model we got in the auxiliary data, and we make the augmented data have those Y's that are consistent with the Z and the X that we created. So that makes sure the marginal distribution of X and Z in the augmented data and the original data that we're appending it to exactly the same. And it's just the conditional distribution of Y given X and Z that we're getting from the data. That's probably really hard to understand over the phone, but it's all laid out in the paper.
Okay, yeah, go ahead, Joe.
Hi, Jerry. This is Joe. Thank you for your talk. Just a couple of thoughts. One thought I had is that it seems to me that what you presented in the language of appending data to data, another way to explain it is you're using one data set to construct an empirically based prior distribution that you are then carrying over to this other distribution. And so you're basically replacing the conditional independence prior, which is a point prior. It says they're conditionally independent with probability 1, and you're putting some spread in that. And I'm just thinking about one thing that Ed said. He mentioned meta-analysis, and I think it might be useful in cases like this when you have data sets that are not necessarily contemporaneous. They're not necessarily measuring the same thing, but they're measuring something similar, to think of them as coming from a population of populations, and to think that, okay, so the parameters that you're building a prior distribution out of from this one auxiliary data set that you've collected. It's not a probability sample. You're using it like glue to glue together things in this other data set. Maybe you're extracting some information from that to create a prior for parameters, but the parameters are not quite the parameters of the population that you're making inference about, but there's something similar to it. And I'm just thinking of formulating it in the sense of that there are lots of populations out there. Each data set is measuring a different target or estimating a different target, but they're all somewhat loosely related to each other. I'm just wondering if that's a useful way to think about it.
Thanks, Joe. That's how I think about it too. In fact, so when I sort of first heard about this adding cases idea, I mean, that's not my idea really, right? I mean, people have been adding pseudo observations to logistic regressions and log linear models, for a while. Sanders Greenland had papers where he talked about adding pseudo observations for computing relative risks. I mean, so this idea has kind of been out there. Taking it into this fusion context is sort of the contribution here. But yes, I completely agree. So when we wrote the paper, kind of introducing it, that's kind of exactly how we motivated it. So if you've got a particular model, and if we said, let's put a multivariate normal down on all the data, then I think you've got well-identified parameters, or not identified in the technical sense, but you've got clear parameters there that you can put down prior distributions on and use the auxiliary data to come up with prior distributions. And the beauty is, you can set those prior distributions. Maybe you've got this data set, it's from 4 years ago. You think the relationship between Y and Z, it's probably around what it's probably similar to what happened 4 years ago, but you want to allow more uncertainty, so you can set a prior distribution that reflects that. If you're going to use kind of a more complicated model, like a mixture model or something where it's not so obvious how to put prior distributions on the parameters, that's where we kind of got this. We were motivated from this augmented cases approach. But you could still think of it like a prior, because basically, you think about how many cases you add as sort of, the prior sample size in some sense. Right? If you want to have, you believe, yes, the relationship between Y and Z is definitely what it was in the auxiliary data. You could add a huge auxiliary data sample size to kind of really force that relationship to go towards that. But if you weren't so confident, you might only add a fraction of cases, fraction of the original sample size, and that will introduce a lot more uncertainty. And so I completely agree. I really like that perspective.
Any other questions? I'm just looking at the time. It's about 2:30, which is when we were going to take our next break. But anything else? Okay, well, great. Thank you guys for a great session and good discussion. Thanks. And I think we come back at 2:45.
Thank you, everyone.
They're going to close in like a half an hour, maybe. Okay. The snack bar is right upstairs. Just go up before you head out to the door, before the little scanner. To your left is the cafeteria.
Oh, so you get it from the cafeteria.
Yeah, that'd be the only snacky place. Unless you go outside.
Don't worry. One of the many things we discussed.